Yeah, so thanks to the organizers for the invitation, because it's a great pleasure to be back here. So I want to talk about the local Tate duality, but or positive characteristics. So of course, the version which I'm going to talk about was given by Schatz in 1964, but there are some issues with the proof, especially regarding the topology of the thing. I'll come to that. And so I just want to say what our approach is to those things. Okay, so let me recall. I'll recall classical Tate duality. Local Tate duality. So what we are having is we are taking K as a local field. And so we are taking A as a finite abelian group, abelian GK module, Galois module, finite Galois module. It's a and we say that with cardinality of A co-prime to cardinality of A co-prime to characteristic of. And we take A prime is a dual, which is Hom A P mod Z. So then the local Tate duality is, if I take Hi of A with A cross H2 minus I of A with A dash, so that maps to H2 of A, let me say GM, which is a Bro group. This is a Bro group of K, which is isomorphic to Q mod Z. And this pairing is, so the theorem is, this pairing is perfect. This pairing is perfect. Oh, yeah. No, sorry. Yeah, right. The mu n, I should have said. GM is what I should have put. Sorry, yeah, thanks. Yeah. Yeah, right. That's what gives you the pairing from A to A dash to GM. Yeah, thanks. Yeah. So this pairing is non-degenerate. A perfect pair. It's a perfect pair. Okay, so that's a theorem in either in, of course, in characteristic 0 it is there, and positive characteristics it works for as long as the cardinality or the is co-prime to the torsion or to the characteristic of K. So right now, so what happens if you are working now? From now onwards, I will take characteristic of K is positive, E greater than 0. And I'll just give an example. Suppose if I take A equal to Z mod PZ, then with the trivial action, then if I look at H1 of Ka, so that's GK of Z mod PZ. And by Artin-Schreier theory, you have infinitely many elements which are, so to any x power p minus x minus small a, where a is not in the image of x power p minus x, you have extension, separable extension of degree p. So, okay, this I should say is here co-prime to the characteristic anyway. Yeah. The Galois group is that of this. Yeah, right. Case separable. In this case. So then, on the other hand, if I take home the dual Z mod PZ to mu infinity, GM, so this is, if I take just maps, there are no elements of P torsion apart from 1. So this is just 1. So then the dual group seems to be trivial. So duality seems to fail. Duality seems to fail. Fails in this case. If I take the naive version of this duality. So the first attempt at how to repair this duality is what this scheme is. Basically, it's given by mu p. If I look at form Z mod PZ GM, and this can be thought of as a group scheme. Over K. So let me recall that if I'm looking at affine group schemes, suppose I've used A for the. So if I have a group scheme G, and let me look at the coordinate ring KG, which is, say, call it B. Suppose it's G is finite group scheme, finite flat group scheme, whatever. Okay. So this amounts to working with B is an Artinian algebra over K. And then you have various maps, the algebra maps and the co-algebra maps. B times the B to K. And the co-algebra, to B, and also the algebra maps and B to B times the B, the co-algebra maps. Yeah, so what you can do is to, you can work with the dual group scheme. So you can work with the dual group scheme. Which also represents a functor. If I look at any scheme S, and that maps to Hom schemes of G cross S to GM cross S. So this is called the Cartier dual, G dual. This is called the Cartier dual. So although as set theoretic, the maps don't exist, the Cartier dual of, so for instance, the Cartier dual of Z mod PZ, D is mu P. Right. So then the proposed Tate duality which you want, the local Tate duality, which is to say that I look at Hi. Okay. Right. Sorry. Okay. So the first thing is to replace our A's by a finite flat group schemes. G. Now, when you're working with a finite flat group scheme, so you'll have to work with the appropriate cohomology. So the cohomology which you're looking at is what would be called FPPF cohomology. So we work with what are called, this underlying site is the Artinian algebras over K. And then we work with the Grothendieck topology. On this category, where the maps, so the maps are families of the covering maps, or families of faithfully flat. Faithfully flat maps. Okay, so this gives you a Grothendieck topology. Now the group G, you can consider it as a finite presented. But in this case, I'm working with Artinian algebras, so everything is coverings are finitely presented. Yeah, FPPF, faithfully flat and finitely presented. Yeah. So finite presentation. No, but everything is Artinian out here, so it's not, it doesn't matter what you do. So it gives you a sheaf on this side. And so what you can do is to, you can finite flat, so you can look at the points of GK, take the functor which, so this was a solution proposed by to the category of abelian groups, and take the right derived functor. So this is my H naught of Kg is my Gk. This is left exact. And take the Hi of Kg is the right derived functors of this. Okay, so then the proposed duality would be to say that I look at Hi of the flat homology of K comma G times H2 minus I flat of K comma the Cartier dual. So that goes to H2 flat of KGM, which one has to say is isomorphic to Q mod Z. And this pairing is perfect. Yeah, so then what is the issue with this? So there is one aspect. Suppose if I take, for instance, say G, is this what is alpha P, which is the kernel of the group scheme, which is multiplication from GA to GA, the multiplication map by P. Yeah, then of course in any reasonable cohomology theory, all the cohomologies of GA vanish. So then you will get that H1K of alpha P is basically K upon K to the power P. Because from the exact sequence for H naught, and the H naught of the GA, final GA will surject onto H1 of the kernel. And this is an infinite group. This is, after all of fields, I can think of it as Fp power series T by Fp to the power P. So this group is infinite. And so when you're taking duality out here, but it's locally compact, so what, let me state the theorem of Schatz. So the characteristic of K, the P greater than 0. So G is a finite flat group scheme. Okay. Then I will state it the same. Then the HI flat KG can be equipped with the topology which makes them locally compact abelian. Making them locally compact. Abelian. And the pairing HI flat of Kg cross H2 minus I out of Kg dual to Q mod Z. So this is a perfect pairing in the sense of Pontryagin. This is a perfect pairing in the sense of Pontryagin duality. Okay, so that is a theorem which Schatz mentions in this article. So that's a, but then around maybe 2010 or something, Mill raised some issues with the way the topologizing this space comes about, and that it's not clear that the topological considerations of the flat cohomology group with the finite flat group schemes have been cleanly done. And then there was some articles after that. So in 2014, there was some article of, I don't know, Bow and Tang. Can't remember the full names, but yeah, that's. And then there's a recent article of Sesnovic. That's in Forum or whatever. Yeah, so I will come to what the problems are when I'm explaining some idea of what the proof is, how the proof goes. So then I will suggest what the solution we have in mind. Okay. So anyway, this is a theorem. So the question is, how do we prove this? Okay, so the proof of this theorem so the point is, so okay, let me say that I'm not going to prove the theorem. So the point is that the flat cohomology, although it's easy to define functorially, following, once you have defined the Grothendieck topology and you have notion of sheaves and abelian categories, you can define it from the point of a homological algebra easily. It's you can hardly do any reasonable calculation with it. So the point is, you can also define, for instance, étale cohomology, and then one knows that étale cohomology is equal to Galois cohomology. So what we have to do is so you have to define what would be called a check cohomology theory for this. All right. So what is what is the check cohomology theory which we have is that in general, if you have B over A is a algebra, so you can have the sequence 0 to A to B tensor B over A. What would be called, I think, the Amitsur complex or what, and so on. And if I take the complex, so some R times, so there are various maps out here into how do I, so B tensor A R plus 1, which is, if I take x0, x1 to xr, then you can, the maps are, you can put x1 tensor 1 at some place, say ith place, tensor xr. This would be called 0 if I'm putting 1 there. And so this would be the maps delta I, which goes from I equal to 0 to R. R plus 1, anyway, whatever. And then we have the co-boundary maps, which here will be called delta. And the delta is, this is what maybe you also call simplicial cohomology or whatever it is. So delta is summation alternating sum of -1 for I. Okay, so that is the check complex which you associate to Artinian algebra. So what you have to do is, given a given a sheaf, F on the space of Artinian algebras over K, so you can apply the sheaf F to this, so you'll be getting F B to F of so, and you can take the cohomology of this. So you can take the cohomology of this complex, and that would be called the cohomology H star B over K, the check cohomology. Okay, so that is so then, so one of the main theorems for which the proof was also suggested by Grothendieck in the Schatz thing, is to say that the flat cohomology H star of Kg, the flat, can be thought of as a direct limit of the cohomologies over H star of L over K of say L F, the relative cohomology. So maybe I should be this thing, let me call this a star check. Okay, I'll at a finite level. So okay, let me I can use say L over K, where L runs over all this thing, K contains finite extensions, L over K finite. Okay, I should just add that if I'm working with, instead of the flat cohomology, if I'm working with étale cohomology of Kg, then I'll be working with separable. With étale, I'll be working with separable. That is not separable. I'm working with K1. That's what I want to say that. So this is going to be limit L contains a K separable and finite of its the standard usual Galois cohomology L over K. F. So this is the usual Galois cohomology which you are used to when you are working with ethyl, but here you have to work with finite flat cohomology for reasons we'll come to it, and with the flat topology, and that gives you this thing. So this is the comparison theorem which you'll have to prove. Yeah. So the way Schatz tries to topologize is to use the check complex which is given out here, which is some, I've rubbed it off. Yeah, no, here, the check complex which is here. And when you're taking the cohomology group, so you're trying to do it at each layer and trying to take the limit. And when you do that, when you're taking limits of, first of all, the topology is not very well behaved when you're working with subquotient topologies and then also taking direct limits. So you run into all kinds of issues regarding the topology or even to say whether the co-boundary maps are continuous. And so these are the problems which Mill raised, that the topology which is being defined and which is in an ad hoc manner, and that is not really suitable for, that it doesn't really justify the arguments. The arguments given are not totally justifiable. Okay, so that is a kind of issue with this proof. So what Sesnevičius did, the problem is the topology on these groups or whatever is given by, these are all G is, I'm taking with G. So G is a Artinian group scheme. I can put it inside some affine space and give a topology for each one of them. Okay. But so I'll be having in general, if I'm working with I'll come to the problem right now, again, in a different context. When you're working with abelian groups or, topological groups, say topological abelian groups, the category is not abelian. You have, co-kernels don't exist, morphisms are not representable and things like that. So you have that, and then you're also taking direct limits of various groups which you don't know what's the correct topology on them. Like, you have the winding line inside the torus. If I take the quotient, what kind of a group it is. So those are the issues which are there. So for instance, in order to define the continuity and other topological properties of these groups, it was not clear what they are. Okay, what Sesnevičius did is, I have not, by the way, this is still work in progress, so take my statements with a pinch of salt in whatever. Is that if you take H1, so what the solution, see, if I look at H0 kg, this is basically, this is finite, so there is no problem with that. H1 kg, he thinks of it as a group of torsors. So then the work by Morey-Bailey and Gell and others, so he uses what is called a topology coming from the stack. Consider it as a stack, and then there is a way of topologizing stacks or local fields, which was done by people like Morey-Bailey and Gell. And maybe I should include Gaber also. And so he was using that topology, and for H2 kg, he was basically higher HIs, basically imposing on it a discrete topology. But he also shows that the topology which you get from the check side is discrete. Okay, so that is so what is the solution we are trying to propose? So to the solution, let me say what the problem is. So I'm going to take a slight diversion and go into cohomology of topological groups. So what happens is if I take G as a topological group, and say, let me take M as a G module, and you want to define H star of GM. So of course, if G is finite, then there are various ways of defining the cohomology. You can either define by projective resolutions or as X groups using injective, or you can also define using cochains. And the initial idea, which for instance for Galois cohomology it works, is that you can define it via the continuous cochains, and you can define like the check definition, which is direct limit of H star of Galois group of L over K with the L invariance, GL invariance. But when I'm working with general Lie groups and other things, so there are issues about how do you define these cohomology groups. Okay, so for instance, if I take continuous cochains, if I take continuous cochains, then M is a topological G module. Yeah, M is a topological G module. So for instance, suppose if I take Z to R to S1, R mod Z. If I take a module, these are the modules which you are taking, and you want to take the cohomology, then if I'm working with continuous cochains, there are no continuous cross sections out here. So you don't even have long exact sequences in cohomology. Okay. So what the correction for that, which was suggested by Moore, was to work with measurable cochains. Which was also, it works, but then it's a horrible theory to work with or to do any calculations. And okay, there are other solutions one can give from the point of view of, one can try to give solutions which are locally continuous at identity, but it can behave anywhere outside. And maybe that cohomology theory is probably good, but we are not going to use that. Instead, we are going to use some ideas, again, going back to Grothendieck. So the idea is, if I'm looking at, say, topological abelian groups or G modules, this category is not abelian. So you can't do homological algebra in the sense of Grothendieck. Of course, so I should say that trying to reinterpret it in terms of topology, Grothendieck theory was suggested by Lichtenbaum, that this is the way one should do it. And it was carried out by Floch in a 2007 or 2008 paper. But Floch's solution is slightly different from what I'm going to give. Okay, so but it's essentially the same. So the idea is then it's via what you would be called a Yoneda embedding. Yeah, while reading it yesterday, I got to know that this lemma was discovered in discussions in Gare du Nord between MacLean and Yoneda on the train. So it's they say the lemma of Gare du Nord, like embedding 1954, August is what some people do. Anyway, so there's a thing called the Yoneda embedding, which is if I take a module M or a group M, I associate to it the functor which the x-valued points of M, which is Fm. So this is a functor to, okay, if I'm working with M as an abelian group, I can say this is a functor from topological spaces. to the category of abelian groups. Okay. Now, under decent set theoretic conditions, that is, if I'm working with some, yeah, so this is, this is continuous maps. Right, I'm working in the topological category, I'm working, so I should say, instead of form, I should say morphisms, whatever is the category. No? So continuous maps, which is, so the replacement is that instead of M, now Yoneda embedding says that, so if I have a map from M to N, so there is a map from Fmx to Fnx, from X to M to M. So you have a, so this is a natural transformation of the functors. Okay, so of course, so what Yoneda's embedding is to say that, Hom of abelian groups, if I want to say continuous abelian groups of M to N, is also the same as Hom of the functors, natural functors of Fm. Yeah, sorry. Yeah. Given M, yeah, given, yeah, X goes to morphisms, which is Fm. Yeah, but this is the functor, so M goes to Fn as a functor. Oh, sorry. M is this thing. M is any abelian group, topological group. There's no discreteness or anything. If I'm taking with G modules, then I would also sheafify G and then think of G as acting on that. I'm saying, suppose if I just considered abelian groups, topological abelian groups, then I will embed topological abelian groups inside what, so I should say that Fm is a sheaf on the collection of, say, topological spaces with respect to, say, open coverings, with respect to the usual topology, usual Grothendieck topology, whatever. Okay. And if I'm having a G module, then I would say that Fmx, if M is a G module, then for each X, I would say that Fmx is a FGX module. And so that's a way of looking at it. I can think of G also as a sheaf of groups over this site. Of course, in order to do all this thing, I have to work with a universe, because otherwise you run into set theoretic problems, and then you'll have to do that. But okay, those parts of homological algebra are somewhat well understood, though not by me, but at least by my collaborator. Okay, so then so what you do is to work with, so you embed your category inside this category, and this category of whatever, so basically what Fm is a sheaf, meaning, so what you get is that these functors from sheaves of abelian groups on the category of topological spaces is a nice enough abelian category which has enough injectives. So you fix a cardinality or whatever uncountable cardinality and fix a universe, and then sheaves of abelian groups on topological spaces. So that's this is an what would be called as a Grothendieck category. Anyway, main thing is, let me just say that it's a category which is, it's a category, abelian category, in which, say, direct limits exist and it has generated. And various things are. Okay, so what happens is that we replace our abelian groups, topological groups, by what would be called sheaves of abelian groups on topological spaces. That's an abelian category on which you can start doing the homological algebra. Okay. So what we do is to so in some sense, to say something is topological is to give a sheaf. So what I'm saying is to say something is topological, topology, is to give a sheaf of abelian groups or sheaf of sets or groups or whatever it is, sets, groups, whatever structure you want, on the category of topological spaces. Okay, so that's via the Yoneda lemma, that is a kind of translation that you take the functor of points associated to the space which you have, and so you work with the functor, and so that is naturally a sheaf, and sheaf homomorphisms are natural transformations, and so the Yoneda lemma says that natural transformations between them, if they are representable, actually comes from actual morphisms of the spaces. So by this. Okay. So now what we are what the solution one is proposing is that, so to look at the flat cohomology, so if I have A is over K Artinian algebra and G is, say, a finite type group scheme, instead of finite flat, I'll work with finite type, say, group scheme over K. The reason I have to work with finite type group scheme is when I have to do the duality, I'll have to work with the multiplicative groups, so I'll have to work with tori. For instance, I have to say that H2K GM is Q mod Z. So I'll have to work with more general thing than finite flat group schemes. I'll have to work with finite type group schemes. And so what happens is, you can you can look at G evaluated at any A. So you can topologize this because I'm working with affine group schemes, so this can be topologized. Because essentially G is an affine, so G will be sitting inside, if it's an affine type group scheme, so I would say it sits inside some capital A and so I can, and it doesn't matter which n I choose, the topology will be still the same. So what happens is, but I think of GA now, I associate to it the sheaf F of GA. So the cohomology which I'm looking at, if I'm given G, I look at F of the map, G goes to F of GK from finite type group schemes. Wait, I don't know whether, let me first work with finite type group schemes. This is an abelian category, one knows. And then to what are sheaves on top, sheaves of abelian groups on top. Sheaves of abelian groups on the category of top. Okay, so that's my, this is what it is. So this is my H naught functor. H naught of K, G, flat. Maybe I should put topology. Yeah, but okay, but I'm going to work with abelian. Abelian, yeah. Yeah, and then I can take the derived functors to this. So now the cohomology is valued. Valued in this sheaves of abelian groups over top. Okay, so naturally, in some sense, the flat cohomology, the derived cohomology gains so-called, so this is the substitute for topology. Topology on the cohomology groups and various other groups. But okay, you can define that. The cup product pairing also exists because you're working with functorial cohomology theories. Of course, you can't do anything because computations have to come via check. So the main theorem, or the first main theorem, is to define the check and show that these two cohomology theories agree. Just like what Schatz has done. So what I should say that from now onwards, the proof is to essentially follow Schatz, but we borrow ideas from Sesnevičius to complete the thing. So, okay. So what we have to do is to also define the check cohomology. So again, if I'm working with an Artinian thing, so you have B to B tensor B over K, B tensor B and so on. And given our group scheme, I can look at the points. Again, all these things are topological spaces. B is Artinian, so B is Artinian over K. But I think of these things as, what do you call, as sheaves. So all these things belong to sheaves of abelian groups on top. All of them belong to that. And then take the cohomology with values in the sheaves of abelian groups on top. So that will be denoted by H check B over A of G. So topological. Okay, so that is a check cohomology which you define. So now I want to say what is the idea of how does one go about proving the duality. So I'm not going to get into the details because first of all, it's messy still. But let me give you some of the main points about what the proofs go on to. So to prove the duality theorem, okay. So one of the main, so before I even get to the comparison theorem, so one of the main techniques is devisage. So what happens is if I work with a finite, G is a finite flat group scheme. So there are basically three types of, three categories which you have, things like additive, which is the alpha phi like alpha p and all. Then you have the multiplicative, which is like things like mu p. And then there is étale, which is when you are working with the GK module, Galois group of separable K module. Those finite flat group schemes which are coming from this. You work with the group algebra with the twisted group algebra with values in the module A. Anyway, so if I have G is a finite flat group scheme, so it has what you can look at the connected component G naught, and I can go to the Cartier dual of G naught and work with this same exact sequence and take dualize again. So what you have is it has something which is multiplicative. So let me say G multiplicative, and then there is a G additive. So this is kind of the structure of, in general, I'm saying this is an example, I'm not saying that. So what happens is the only simple additive finite flat group scheme is alpha p. Similarly, the only simple multiplicative finite flat group scheme is mu p. Okay, so all of them will have filtrations. So if I'm working with additive groups, then you will have filtration so that all the subquotients are alpha p's, and you can have it for the mu p also. Okay, so that is so the first step is, so the devisage will be used again and again at some point or the other to reduce it to alpha phi, mu p, or the étale cases. So that still doesn't solve the issue. So probably the key step or the really difficult step, in some sense, one of the difficult steps is a comparison theorem. Which is to say that if I work with H star flat topological of Kg, so that is like whatever we said. Okay, so I have to say that, yeah. So G is a finite type group scheme. And that is the limit for L contains at A bar, A lower K finite of H star or the check topological of L lower K G. This is a direct limit, I should say. This is. Anyway, this is, yeah. So as a corollary for this, I should say that some of these things are, of course, one has to do it in a topological context, and that gives us additional work to be done. I'm saying, of course, even in Schatz himself says that suppose if I take G is smooth, if G is a smooth group scheme, then one can work with H star flat of Kg is the same as H star étale of Kg. In particular, for instance, if I work with G, say Gm, and then H star étale of Kg topological of course, whatever it is, not this thing. So that's a Galois cohomology, say a star of the Galois cohomology of K with, say, for instance, if I'm working with GM, K is GM, and this one can show is isomorphic to the Brouwer group. This is a classical Brouwer group of this scheme also. Okay, so that's how one tries to get hold of what is H2 in some sense, that we work with, if it is finite, then one reduces in some sense to the étale case. Okay. So that takes care of the H2 of the one which is there. So the next thing is, so apart from the Davis arc, there are two more important theorems which we need. So for instance, we have to say, so we have to say that the cohomology groups which you get are nice. The check cohomology groups. Okay. Let me say a few words about the proof of this comparison theorem. Why it is difficult. The point is to work with. So we have to say that these two sides are. One has to say they are connected, exact, and universal functors. That is a check and the other things on the category of Artinian group scheme, on the category of finite type group schemes. Finite type group schemes. This is the abelian category of finite type group schemes. So let me say that the flat topology is universal on the category of all flat sheaves on over K, but not necessarily restricted to the smaller abelian category. Okay, so although one knows it's connected and exact, but we don't know the universality on this smaller category. So that has to be done. The check runs into a problem, which is to say that, sorry, just 2 minutes. If I have a morphism of G dash to G double dash to 0, short exact sequence, then I have to form the check complex C dash to C dot G, the check complex C dot G double dash. And one can say that this is left exact, but then the main thing is to say that it's surjective. Yeah. So this is, of course, the problem which Schatz also has to solve. Schatz does it at the group theoretic level. So what we have to do it is at the topological level. One has to do. So which means basically you need to produce cross sections, continuous cross sections. Okay. So here we make use of two basic theorems. One is the theorem of Morey-Bailey and others whom I said, that if you have a G to H is a smooth morphism, then the map from, say, GL to HL, this is open. Okay, so that is one. And then the other thing which we need is a old theorem of Michael on cross sections if things are profinite. Okay, so when you use this kind of theorems, then one can try to show that n plus some whatever are the arguments which is effaceability is clearer in the check context, and then you do some dimension shifting to prove the comparison theorems. And for proving the duality, essentially what you do is we reduce it to the alpha p, mu p, and et al. Case. For the alpha p and mu p, it's the duality is kind of by explicit computations. And for the et al. Case, we have to do the multiplicative Tate-Nakama duality and then reduce the duality in this case. But again, the problem is, abelian-wise things have been worked out in shacks, but we have to do it in the topological context all the time. So for that, which, apart from More-Bailey, this paper of Sesnovičius has come in of use, where we adopt some of his arguments to this case. So that is the thing which is not yet complete, but we are hoping to get it done soon. Yeah, that's.
Any questions or comments? Yeah.
Right. Yeah, it is a sheaf. We can, because it's a Grothendieck category, so you can take the direct limit. So it's as a sheaf we are working with. It's also a sheaf. Everything is, the derived functors are taking values in sheaves of abelian groups on topological. Both are sheaves, yeah. Yeah, right. Yeah, so in some sense, right, more generally, like, if I'm even working with schemes or whatever it is, the cohomology of a scheme is a sheaf valued on the category of all schemes. So it's very close to what, what is happening in condensed mathematics. Right. But yeah, but these things on cohomology of topological groups, I had these things since around 2005, 2006, but Floch had written it up, so I didn't write anything of whatever I had because it was. Floch also does it, but then he calls it internal home in his compositor 2007 or 8. So he deals with cohomology of topological groups in the style of Grothendieck. And within few pages, 3-4 pages, he covers all the basic theory. But he still works with abelian groups, but he says these are what may be called, they have a topological structure, but he doesn't say it in the category of this notion, but it's kind of somewhat similar. But unfortunately, I think only the condensed mathematics is there, but condensed mathematics is a bit more complicated. I think here it's a much more basic notion of using Yoneda's lemma to shift to an abelian category. Yeah, there are other motivations for doing the condensed mathematics, which is there. So it's more closer to that. Yeah, there is a paper by Kolmes and Niziol also on using condensed mathematics to do some duality in a different context, but yeah.
Any other questions or comments? If not, let's thank Rajan again.
Yeah.